Hello and welcome to my presentation on a voltage-controlled Magnonic crystal at a submicron scale. In the following I'm going to show you how we realized the Magnonic crystal based on the periodic modulation of ferroelectric domains in a multiferroic layer which controlled the propagation of spin waves in the ferromagnetic layer below, as you can see here on the right hand figure showing a band gap occurrence at a specific frequency. Let me first start my talk with acknowledging the contribution from our entire team, especially in the Magnonics group from Hugo Merbush, who recently moved as a postdoc to Münster, and also Victor Haspot, who contributed strongly to the oxide growth and the characterization, and of course everyone else contributing to this work. In addition, I would like to acknowledge the funding agencies which enabled this work, namely the FET Open Project Chiron in the realm of the Horizon 2020 program, and also from the Roseau project from l'Agence Nationale de la Recherche from the French government. So Magnonics is a research field where we try to encode and process information in magnons, which are the quanta of spin waves, specifically speaking the quanta of collective spin excitations in a magnetically ordered material where two neighboring spins exhibit a fixed phase relationship and are precessing around the axis of saturation magnetization. Magnonics has the prospect to solve several problems of contemporary electronics, which is right now reaching its fundamental limit, also for devices operating at the gigahertz scale and the sub-millimeter scale, and no further downscaling, such as to a nanoscale, is possible, also because it's hindered by parasitic Joule heating, which is originating from the translational motion of electrons in these systems. On the other hand, Magnonics could operate on the nanoscale, as it could have wavelengths down to 10 nanometers, has a wide range of operating frequencies from the sub-gigahertz scale to a terahertz scale, and since there is no electronic motion involved, there would be also no additional Joule heating. Among Magnonics, Magnonic crystals are especially interesting for applications, as you will see, and they are describing artificially tailored magnetic media with a periodic variation of a physical parameter controlling the spin wave's properties. It can have two types of branches of applications, which is one for digital data processing, specifically spin wave logics as the building blocks of computers, and we could think of, for instance, of transistors using a Magnonic crystal or Magnonic majority gate. On the other hand, we can use it for filtering in analog data processing, where we use it to filter out frequencies in the radio frequency regime. So here I'll show you one example which has been realized by from TMAG et al. A couple of years ago, which is a Magnon transistor. And it is based on a Magnonic crystal which has been realized by permanently implanting grooves in a YIG film, where we can now use the control of the gate by the Magnonic crystal to suppress the source to drain current from the source magnons as they propagate through. The Magnonic crystal comes with a strong localization, and this enables a high scattering probability of the source magnons to the gate magnons, and the secondary magnons, which are generated as a result of these nonlinear processes happening there, have a large wave vector and a small group velocity, and thus are prohibited to flow out of the gate region, which results in a strong suppression of the corresponding source to drain magnon current. However, in order to benchmark them against CMOS-based technologies, we have to achieve fully tunable and reconfigurable systems on demand, and also filtering is especially important, as Magnonic frequencies, which are typically in the tens of gigahertz, also could be used for the radio frequency band of 4G and 5G telecommunication systems. However, let's start with how the filtering by the Magnonic crystals works, which is mostly done by some form of spatial filtering, but in principle you can achieve a Magnonic crystal by doing a periodic modulation of any physical parameter which is governing the spin wave properties, and we can use then the effect of fulfilling the Bragg condition for constructive interference of different layers, as you can see, of the periodic system. So if we now look, for instance, the typical spin waves in the Demon-Eschbach configuration, where the externally applied static field is perpendicular but in the same plane to the wave vector of the propagating spin waves, we can see that in the absence of any modulation, we don't see any opening of the gap. So this is here shown by the red dotted line and the enlargement. However, if we now induce such periodic modulation, we see the opening of a band gap, which is characterized by a zero group velocity inside the gap and, of course, non-zero group velocity outside the gap, which is then the hallmark of the occurrence of a Magnonic crystal. How do we observe this experimentally? We do spectroscopic measurements where we measure the transmission amplitude of our spin wave and also the phase signal by using vector network analysis. And we can see that in the band, at the frequency of a band gap, we see a strong drop in the transmission amplitude of a spin wave, which is accompanied by an additional jump in the phase spectrum because of the discontinuity of the group velocity, which is related to the phase measurement. Magnonic crystals have, of course, been already studied extensively in the past, and we can divide them, the existing waves, into two parts. So one is fixed and static Magnonic crystals, where you do a permanently implantation of grooves or using ion beam implantation on ferromagnetic films, and you obtain a suppression at the respective bandgap frequency corresponding to the periodicity of your system. Or people tried to realize dynamic Magnonic crystals to fulfill the tunability and reconfigurability of these demands. Where one approach was, for instance, to use laser to induce a thermally induced landscape, which is periodic modulating when the system's spin wave properties, or using a Mender-like structure, where you flow a current through, and you also control the internal film's field, which is controlling the spin wave propagation. However, the problem with these approaches so far is that they're either static, rubber bulk, or require external sources such as lasers and fields, and hence have a limited tunability and power efficiency. We, however, need Magnonic crystals for logics and filterings on the nanoscale, and also realize the voltage control for the integration of benchmarking of CMOS-based technologies. Regarding the nanoscale, in an earlier work, Hugo has shown that we can do filtering with Magnonic crystals for nanomagnonics, where we had a 20 nanometer thick width modulated YIG film, as you can see both here in the sketch on the left-hand side and the photograph in the middle, with a low magnetic damping. And we could show that we have an efficient filtering with a frequency selectivity of 20 GHz at an operating frequency of 4.9 GHz. And it was possible to do a phase resolve detection of a spin wave by using microfocused Papillon light scattering spectroscopy. And based on the analysis, it's now possible to extract both a real and imaginary part of a wave vector for any type of Magnonic crystal as shown in this work. So this was the realization of a nanometer size static Magnonic crystal. However, what about now to go a step further and to obtain a reconfigurable and tunable Magnonic crystal on the nanoscale, and also to introduce some voltage controlled system? So if we now think for materials for tunable and reconfigurable Magnonic crystals, of course, the crucial parameter in such Magnonic applications is to have the smallest possible Gilmore damping parameter to obtain larger propagation distances and larger amplitudes as well. Terminal, which is typically used, has a large damping parameter, so it's not good enough for our needs. And so far, as also from the examples shown before, mostly yttrium iron garnet has been used, which is also some kind of benchmark material of the Rossfilia in Magnonics nowadays, as it has the lowest known Gilbert damping for a ferromagnetic system, which typically in alpha lower to the 10 to the power of -4. However, the growth is rather limited, as it mostly goes on other garnets as well. But if we now go to other systems, such as oxides, they have several advantages over a system like YIG, where we can now try to use and exploit the interface effects in oxide heterostructures. And our heterostructure of choice was a lanthanum-junction manganese system, which is a ferromagnet, and is ideal for propagating spin waves due to its high Curie temperature and the relatively low Gilbert damping parameter, and bismuth orthorite, which is so far the only known multiferroic system connecting the magnetic and electric degrees of freedom internally for free at room temperature. So here is a short overview of the materials we used and the material and the stack of our heterostructure. And we can see that, as I said, bismuth ferrite is multiferroic, it is antiferromagnetically ordered and exhibits ferroelectricity. As LSMO, it's a perovskite, and both of them have comparably high Curie temperatures in the order of 1100 Kelvin and 370 Kelvin, respectively. The films have been epitaxially ground by pulsed laser deposition. And it has been already shown theoretically that indeed such multiferroic ferromagnetic heterostructure can have an effect when you change on the spin wave propagation or the control of a magnetoelectric coupling by changing the ferroelectric domain polarization. As you can see here from your study, showing that if you change your polarization state, you can modulate as well the magnetoelectric coupling between the ferroelectric layer and the ferromagnetic layer. In addition, another group has tried to has performed micromagnetic simulations with using voltage controlled magnetic anisotropy, whereby the control of anisotropy also controls again the spin wave properties and enables, when you apply a voltage, to go from a system where you see no band gap occurring, you see the occurrence of band gaps when the voltage is applied. So you do modulate your system. So this shows from theory that there is a magnetoelectric coupling in the interface which can be used as the ferroelectric domains can change the magnetization properties of the ferromagnet. So this is what we're now going to do. We did such experimental demonstration with our BFO here, LSMO heterostructure. So we had this heterostructure was ground in situ with 30 nanometers of LSMO, and on top of that we had 23 nanometers of BFO, which was as ground down polarized, here shown by the arrow. We did first ferromagnetic resonance characterizations, where you can see that we had a low Gilbert damping parameter of an order of 6 times 10 to the power of -3, and especially important, and also important, low inhomogeneous broadening in the order of 3 Gauss at room temperature. So the experimental setup one was the following. We patterned and microwave antennas on the films with a periodicity of 500 nanometers and used propagative spin wave spectroscopy to measure the spin wave transmission spectrum using vector network analyzers and deduced the inductance in our system. We used then later on piezo force microscopy to change the ferroelectric domain state in our heterostructure stack. So, as I said, we did first write uniform domains in the area between the antennas, as you can see here by the photograph showing the 2 antennas, and then the down polarized as ground state in this small inset, and then we changed from the measured the spin wave transmission, and then we changed back and voted up polarized state, here shown by these images as well, and then compared these two in terms of amplitude, here shown the upper figure, and in the imaginary part shown by the lower figure. And you can see that qualitatively there is no difference between these two spectra, which means that the uniform states do not have any qualitative change on the spin wave propagation transmission measured between the two antennas. In addition, afterwards we did of course write a periodic state after writing the up state, and then we reversed our entire system to a down polarized state again, as it resembles most to as ground state, and you can see that we again see no features of some band gap occurring in the structure. The transmission spectrum looks really similar to the spectrum from the uniformly polarized state, which means that we can have a reversible ferroelectric domain state, and since there's no change in the spin wave transmission of LSMO, we can attribute any change now to the periodic modulation in our system. As you can see here now, we did write periodic domains with a periodicity of 500 nanometer, which corresponds to the periodicity of antennas, maximizing the observation of our band gap. And we can see that we see in the amplitude spectrum, as expected, a strong drop at the frequency of a band gap of in the order of 20 dB, which is as predicted accompanied by this additional jump in the phase spectrum. So we realized with such heterostructure Magnonic crystal by the periodic writing of ferroelectric domains. So what is then, of course, we are questioning what is the governing physical process in the system. It cannot be electron or oxygen migration because we see a non-volatile PFM contrast over subsequent PFM writing steps. And so one possible reason is, which needs to be further investigated, of course, is that we have some exchange bias for the uniform ferroelectric polarization states. It has been already shown, and there are known such BFO LSMO heterostructures to exhibit some magnetoelectric coupling by such exchange bias. However, it has been measured microscopically, and there it vanishes down up to room temperature and goes to 0. However, we think that due to the small mass of our domain size, so basically we have periodicity of 500 nanometer and domains of 200 and 300 nanometer for the individual ferroelectric domain written, that we have a small remnant exchange bias which is non-zero and then thus enables the modulation of a spin wave in the LSMO layer below. However, this needs to be further investigated, and for instance one could start with an LSMO thickness dependent study doing the same experiments to understand further the impact of the interface between the BFO and the LSMO. With that, I would like to summarize my talk. So I have shown you the experimental realization of a Magnonic crystal. We have multiferroic-ferromagnetic heterostructure which inhibits the properties of being reconfigurable and reversible. So we have a persistence of a spin wave amplitude over several writing cycles. It is tunable because we could easily tune the gap frequency by writing various periods with our piezo force microscopy technique. And also it's rather compact, and we do not need additional lasers, for instance, in our system. So thank you very much for your attention.